7 comets, more than we usually see in a decade, are plunging into the inner solar system right now. Astronomers are calling this a once-in-a-century swarm, with objects so bright that even Earth's ancient sky watchers would have been awestruck. Yet in this cosmic spectacle, the interstellar visitor, 3I/Atlas, isn't even the brightest. There's a comet forecast to outshine them all, challenging everything we thought we knew about cometary encounters. Why is this happening now, and what does it mean for our planet and the sun? The answers could reshape our understanding of the solar system if you're ready to follow every twist in the sky. The first wave of this comet swarm set the outer boundary back in late July. C/2022 N2 Pan-STARRS, discovered by the Pan-STARRS survey in Hawaii, reached perihelion on July 31st at a distance of 3.82 astronomical units from the Sun. That's well beyond Mars, and for most amateur astronomers, Pan-STARRS was a telescopic target, faint, steady, and serving as the opening act for what was coming next. Just weeks later, the action moved sharply inward. C/2025 R2 SWAN, flagged by an amateur scanning solar wind camera data, swung in for perihelion on September 12th, passing only 0.50 astronomical units from the Sun. SWAN's real headline, though, is its close approach to Earth. On October 21st, it will pass just 0.253 astronomical units from our planet, or roughly 38 million kilometers. That puts it among the closest comet flybys of the past decade. Astronomers are watching for possible outbursts or tail disruptions as SWAN nears both the Sun and Earth, with brightness forecasts suggesting it could flirt with naked eye visibility under dark skies. Meanwhile, 414p/stereo adds a wildcard to the mix. Its orbit is still being pinned down by spacecraft data, but most estimates place its perihelion between September and October, with a likely minimum distance to the Sun somewhere between 0.5 and 0.7 astronomical units. Unlike the others, stereo is best seen by solar observatories, not from Earth. Its behavior remains unpredictable until more data arrives, highlighting the challenge of tracking so many comets in such a short span. This opening trio sets the stage for the deeper dives and brighter surprises still to come. Now the real drama begins as the next wave of comets plunges even deeper toward the Sun. C/2025 K1 Atlas is first up, discovered by the Atlas survey in Hawaii. Its perihelion comes on October 8th, and this one gets closer to the Sun than Mercury ever does, just 0.33 astronomical units. That's less than 50 million kilometers, a region so hot and turbulent that many comets simply don't survive. Atlas has a history of sudden outbursts, and astronomers are watching for signs it could fragment or even disintegrate as it rounds the Sun. If it holds together, there's a brief window for binocular viewing, but the real risk here is that it might vanish in a final flare. Then, as the calendar turns to November, all eyes shift to C/2025 A6 Lemmon. This is the comet that has everyone talking. Discovered by the Lemmon survey in Argentina, it stunned observers with a rapid brightening earlier in the year. Perihelion is set for November 8th at 0.53 astronomical units, and forecasts from both professional and amateur networks now put its peak brightness at magnitude 3 or even 4. That's bright enough for naked eye viewing, especially from dark locations. Lemmon is expected to stretch a classic, glowing tail across the sky, making it the most spectacular comet of the swarm, a true main event for sky watchers. The anticipation is building, with observing campaigns already underway on every continent. Finally, rounding out the year, 240p/NEAT makes its return. This is a known periodic comet, swinging closest to the Sun on December 19th at 2.12 astronomical units. NEAT won't be a showstopper. Its brightness will stay in the telescopic range. but it completes this remarkable sequence, reminding astronomers just how rare it is to have so many significant comets in one season. With Lemmon poised to light up November skies, the stage is set for a dramatic finish before the focus shifts to what happens when these icy visitors meet the full force of the sun. Every comet that swings into the inner solar system reveals its presence with a dramatic tail. But there's more going on than just a streak of light. Comet tails actually come in three main types, each shaped by the sun's intense influence. The dust tail is made up of tiny solid particles, bits of rock and ice released as sunlight heats the comet's surface. These grains are pushed away from the comet by the pressure of sunlight itself, forming a broad, curved tail that glows in reflected light. The ion, or plasma, tail is a different story. Here, charged gas molecules get swept directly away from the sun by the solar wind, a steady stream of charged particles racing outward at about 400 kilometers per second. This tail always points straight away from the sun, no matter which way the comet is moving, and it often glows blue from energized carbon monoxide ions. There's sometimes even a third, faint tail made of neutral sodium atoms, barely visible but detectable in sensitive images. The sun's magnetic field wraps around these tails, shaping and sometimes even snapping them off during solar storms. By watching how a comet's tails respond, astronomers can actually map invisible forces in the solar wind, turning each comet into a kind of space weather probe. Coronal mass ejections, or CMEs, are the sun's most explosive outbursts. Giant clouds of charged particles hurled across the solar system at millions of kilometers per hour. When one of these eruptions slams into a comet, the effects can be seen in real time. Back in 2007, astronomers watched as a CME struck Comet Encke. Within minutes, its plasma tail was sliced clean off and swept away, only to regrow as the comet pushed onward. These tail disconnection events aren't just dramatic. They're a goldmine for space weather science, revealing how solar storms ripple through the inner solar system. Now, with so many comets diving close to the sun during solar maximum, the stage is set for even more spectacular encounters. NASA's Parker Solar Probe is flying inside the orbit of Mercury, less than 0.1 astronomical units from the sun, and it's poised to catch these interactions up close. Missions like Parker and the European Space Agency's Solar Orbiter are coordinating with ground-based astronomers, ready to pivot when a CME targets a comet. Every tail snap, every outburst, becomes a live experiment, helping scientists model the invisible forces shaping both comets and the solar wind. The next few months could deliver some of the most valuable space weather data in decades. Inside the coma of 3I/Atlas, the numbers almost defy belief. Recent measurements from the James Webb Space Telescope put its carbon dioxide coma at 700,000 kilometers across, half the diameter of the sun. That's not just record-breaking for an interstellar visitor. It's a scale rarely seen even among the solar system's largest comets. Yet the true heart of this object remains hidden. Estimates for the nucleus size are all over the map, from as small as 5 kilometers to more than 40, depending on how much dust and gas is masking the core. JWST's spectral data reveal a chemistry dominated by carbon dioxide outgassing, with only faint traces of water ice and almost none of the cyanogen or carbon monoxide signatures typical of local comets. This points to a body forged far from our sun, carrying the fingerprints of another planetary system. But every new observation seems to raise more questions than it answers. Is the nucleus shrouded in a thick mantle of dust, or is it simply smaller than anyone expected? Right now, even the world's most powerful telescopes can't say for sure. For scientists, 3I/Atlas is both a laboratory and a puzzle, an active interstellar comet whose secrets are still locked inside that vast, glowing shroud. A dust trail from 3I/Atlas is now the subject of intense modeling, with predictions pointing toward a faint meteor filament crossing Earth's orbit in March or April 2026. Most simulations suggest the debris will be sparse, tiny grains drifting through space, unlikely to spark a major meteor shower, but enough to keep all sky cameras and radar networks on alert. For planetary scientists, even a handful of interstellar meteors would be a breakthrough, offering the first direct samples of material from outside our solar system. Beyond the science, the arrival of so many comets in a single season echoes through human history. Ancient chroniclers saw these sudden visitors as omens, warnings of war or change, carefully recording their appearance in clay tablets and medieval manuscripts. Today, astronomers still feel a sense of AW and unpredictability. No matter how advanced the models, comets can surprise with outbursts, disintegrations, or unexpected displays. ESA's Mars orbiter is already booked for a November imaging slot, aiming to capture 3I/Atlas from another planet's vantage point. The legacy of this swarm will stretch from meteor trails on Earth to new perspectives on the ancient stories written in the sky. In 2025, 7 major comets will reach their closest point to the Sun within just 6 months, a frequency not seen in decades of modern sky surveys. This swarm includes C/2025 A6 Lemmon, forecast to reach magnitude 3 or 4 and offer rare naked eye views, as well as 3I/Atlas, only the third confirmed interstellar comet, with a coma spanning 700,000 kilometers. Despite new data from observatories and spacecraft, key questions remain. The true size of 3I/Atlas's nucleus is still uncertain, and whether its dust trail will produce a meteor display in 2020 is not yet confirmed. Scientists are closely monitoring how these comets interact with the solar wind at solar maximum, using past events like the 2007 Encke tail disconnection as a benchmark. The Vera Rubin Observatory and planetary missions are expected to expand our knowledge even further. The events of 2025 will give astronomers and the public a unique opportunity to observe cometary science in action and challenge what we know about the solar system.